So now that we've explored how to work with means in the simplest case, I want to introduce a far more likely scenario. We're still working with means, but in most cases, the standard deviation or the variance of the population is not available. This is an example of some data that came from a research study that looked at cell phones and sleep. The idea being that the blue light on the cell phone actually resets our circadian rhythms, disrupting quality of sleep. We know in general that the average American gets about 7.5 hours of sleep a night. So what researchers did is they looked at the number of self-reported hours of sleep of people who use their cell phones shortly before bed. You'll notice that compared to almost all the previous examples that we've talked about in this class, we don't have access to variance or standard deviation of the population. We don't have it. We can, however, estimate it. But what are we going to estimate it from? Well, we have a sample of data from the population. We have a sample of 10 people, and we can calculate the variance and standard deviation of that data set. Maybe we can use that to estimate the variance of the population. And sure enough, there is a mathematical relationship between the variance of a population, right? So this top row here shows the distribution of data across different data sets, and the variance then represents the spread, the kurtosis of each of these data sets. And what you find is that samples taken from any of these distributions are going to have a variance that looks similar to the variance from the population distribution it comes from. But it's not going to be perfect. There's going to be bias that is introduced whenever we are trying to estimate the variance of a population based on a sample size. This might sound familiar to some of you because we talked a little bit about this in a previous chapter, which is when I told you when we're calculating variance, normally we take the sum of squares and divide by the sample size. But you will sometimes see the sum of squares divided by n minus 1. Right? This is when we are trying to take a sample and estimate the variance of a population. So if we are not given the variance of the population, instead we can take the sum of squares of our data and divide by n minus 1 instead. This n minus 1 is an important value that refers to what we call the degrees of freedom. The degrees of freedom is the number of items in a list, or the number of numbers in a list of numbers that is free to vary. Right? Let's look at this in an example other than numbers. I think something fun to look at is hats. So what we have here is we have 7 hats, and if the only constraint is that we cannot wear the same hat twice in a week, how can we make our decision? Well, if we start on Monday, can we choose a hat to wear? Sure, we can choose any hat we want. Maybe we'll wear the witch's hat on Monday. On Tuesday, can we make a choice of what hat we want to wear? Sure, let's wear the top hat here for Tuesday. And maybe Wednesday the Santa hat, and then the cowboy hat on Thursday. Right? Friday we wear the beanie, and then now we have the crab hat and this little conductor hat for Saturday. So we'll pick the crab hat for Saturday, and now we're left on Sunday. Do we have a choice of what hat we can wear for Sunday? Well, we've picked 6 hats for 6 different days. We don't actually have a choice. Because of our restriction of being able to only wear 1 hat per day per week, we have to wear the conductor hat on Sunday. There's no choice. So, for 7 days of the week with 7 hats, there are 6 days that are free to vary. There are 6 days that a choice can be made, so we'd say that the degrees of freedom in this case is 6. This is the same idea that holds true for our list of numbers. Generally speaking, our degrees of freedom are calculated as n minus 1. Right? N minus 1 determines the number of numbers that is allowed to vary in our data set. So when we're calculating our estimated variance, what we're really doing, we're dividing the sum of squares by the degrees of freedom. Right? The degrees of freedom is n minus 1. So this is used to estimate the variance of the population from our data set. Once we have that, we still have to work with means, right? Because remember, we're working with hypothesis testing of means. So we're not done yet. Once we have calculated our estimated variance, we still have to go back and do what we just learned, which is we have to divide that estimated variance by our population. We have to divide that estimated variance by our sample size. And this is just what we did in the previous video, except we've now added the step of estimating the variance first. We can then take the standard deviation of that, and we have the standard deviation distribution of means, and now we can move forward in calculating our significance test. The problem is that estimating the variance, you lose accuracy. It's not as accurate as if you actually know the exact variance of the population. Because of that, we have to adjust our thresholds. We are no longer doing a z-test, and instead we are doing what is called a t-test, or the student's t-test. And instead of using the z-table and the z-distribution, we use the t-distribution. It turns out that the t-distribution becomes closer and closer to the z-distribution as degrees of freedom go up. The smaller degrees of freedom, the further away it is from the z-distribution. At an infinite number of degrees of freedom, the t-test and the z-test are the same. But we're not going to have that. We're going to have to use the t-table to determine what our cutoff is. We still determine an alpha, 0.05, 0.1, 0.01, whatever you want, but instead of going to the z-table, we need to go to the t-table. So here's how the t-table works. We first decide, are we doing a one-tail or two-tail test? And that should have been established when we set up our hypotheses. If we're doing one-tail, we go to the one-tail column. Two-tail, we go to the two-tail column. We determine our threshold by looking at the degrees of freedom. So, for example, I had a sample of 10. My degrees of freedom would be 9. So my cutoff for 9 degrees of freedom at an alpha of 0.05 is 1.833. At an alpha 0.01, it's 2.822. So the t-table is divided into one-tail and two-tail, and then we look it up based on the degrees of freedom. Once we have the degrees of freedom, we look at the corresponding threshold for the alpha we have selected, and then we do the t-test. The t-test is going to be the exact same core calculation that we did for the z-test, except now we are using the standard deviation of the distribution of means based on the estimated variance. So the t-test is going to be the mean of our sample minus the known mean of the population divided by that estimated variance. So it's the same calculation as the z-score, except now we're using the estimated variance instead, and we're using the t-table to determine the threshold.